Hi, this video we are going to look at example now for determining moment of inertia. The previous videos we look at for common shapes like rectangle, triangle, circle when we introducing the polar moment of inertia. Then right after we introduce the parallel axis theorem. Now we're going to combine all those things together to solve some problems. As you can see for this problem, you have this shape right here. They want us to find the moment of inertia with respect to this bottom x-axis. In order to do that, you can see there are a few common shapes. First one, you see this rectangle right here. Then we're going to get rid of the semicircle. Then we can solve this particular shape. But you realize I want you to pay attention on this 2, the shape number 2 here. You notice they still have 2 that's suspended in the air because with respect to x-axis here, that's where the semicircle is located. And that's important because why? We're solving with respect to this particular x-axis that have to be staying consistent. So if this is our strategy, we're going to use rectangle moment of inertia minus the semicircle one. Let's go ahead and start. So first step is we're going to try to solve this I for this rectangle regarding x-axis. And do we have a formula already? Indeed, right? We already know it's 1/3 regarding the base, right? Regarding the centroid, however, it's different. It's 1/12, but here it's regarding the base x-axis. So it's 1/3 bh cubed. And what's our b? Our b is going to be our 240. And our h is 120 cubed. So you can go ahead and solve that. So what I have over here is quite a huge number. It's 1.3824 times 10 to power of 8. That's a huge number, isn't it? That's millimeter to the 4th, okay? That's moment of inertia unit. It's 9th power of 4. Now the second step is we're going to solve this I semicircle with respect to this x-axis. And like we talked about earlier, this is suspended semicircle, right? It's like a floating above x-axis. So immediately we were thinking about how about we use parallel axis theorem, right? Because we do know a few things. We do know the semicircle moment of inertia regarding its base, do we? Okay. All right, so here I go ahead, copy paste the common shape from your textbook. And as you can see for the semicircle, it's on there, and I can zoom in a little bit better. So we learned about before for circle is ix y equal, they're equal to 1/4. And for semicircle, it's going to be just half of that. So that's going to be 1/8. So knowing that, we'll just say, we do know this semicircle. If I were to draw this semicircle in that particular orientation, and however, we are looking at regarding its base, which is right here, right? Then we know that x. We know this value, our ix, is equal to 1/8 pi r to the 4th, correct? Okay. However, we do not know regarding this new axis, which is in this particular orientation would be somewhere here, right? So how do we do that? Can we use parallel axis theorem right off the bat here? We might be tempted to do it, but that would be incorrect. Why do I say incorrect? Remember parallel axis theorem? You have to know what? You have to know the moment of inertia regarding the centroid. Is this x here is the centroid? No, it's a base. Where's the centroid at? Centroid is right here. The centroid for semicircle we learned it's somewhere close to the base here. That's going to be the centroid. So if I were to draw that using a different color, that's going to be your centroid. That's your x prime. Okay? And if I call this x1 here, and this I'm going to call x because that's where we want to solve. So in order to solve so here I'm going to label ix1 here. In order to find, so here's our logic. In order to find ix, we need to find ix prime, which is the centroid axis. So here, make a note. X prime here is the centroid axis. Because we can only use parallel axis theorem when we know the moment of inertia regarding central axis. So first step is we need to find that. Once we find that, then we can go ahead and find ix. So that's our two-step process. In order to find ix prime, we're going to use parallel axis theorem reverse way. So go ahead and let's try. Because we do know ix1, this new axis, is going to be equal to ix prime plus a d1 squared, and this is our d1. Okay, ix1, that's regarding base, which is 8 pi r to the power 4th. And we're solving ix prime. We know the area of a semicircle is going to be pi r squared over 2. Then what's our d1? Remember, this x prime going through the centroid. Review our centroid topic. For semicircle, that distance is equal to 4r over 3 pi. Okay? And that's going to be our d1, so it's 4r over 3 pi. And don't forget, it's square. So from here, we can definitely solve ix prime. Don't you wish that this value is actually showing on our table in the book? However, it's not there. But once you have down this time, you can go ahead and put in your textbook, okay? So it will be pi r to the power 4 divided by 8 minus. So let's go ahead and solve that. You have pi r. I'm going to start to put them together. Let's see if we can do that or not. So I'm going to have a scratch paper here. Okay, so this is my pi r over 2, and here will be 16 r to the 4th 9 pi square. Then pi cancel out, then 2 cancel out here, then we will have 8. Okay, all right, so we'll have 8 r 8 over 9 pi r to the power of 6. Oh no, that's not right. This is power of 2. I said like that shouldn't be power of 6. Okay, so that will give us power of 4. Okay, 8 over 9 pi times r to the 4th. So I'm going to bring that one right here. So it will be 8 r to the 4th over 9 over pi. Okay. All right, so that's going to be our ix prime. If you want to continue simplify it, I can take r to the power 4th out, and inside parenthesis will pi over 8 minus 8 over 9 pi. Okay, so that can be a formula you can put in your book. Around here you can see I centroid or ix prime, what they're equal to. Okay, all right, now our next step after finding ix prime is finding this ix. We're going to use parallel axis theorem the second time. It's going to be equal to ix prime times a d2 squared. All right, since we already just found ix prime, so it's r to the 4th pi over 8 minus 8 over 9 pi. Then plus our circle, our semicircle area is again pi r squared over 2. Then this time d2 is going to be from this centroid x prime to this new x-axis where we are solving, right? Basically from here to here. That's going to be our d2. Then how do we figure out this distance? We know this entire length is 120, and we know the d1, so we know d2 will be this 120 minus your d1. Again, d1 is our 4r over 3 pi. So that's going to be our d2 in parentheses, and don't forget, it's squared up. So that's going to be our Ix, and make a note, this is Ix for this semicircle, right? We find for rectangle already. Now I'm just going to do my heavy duty math here to get out this value. Let's take a look at what's our R. R is 90. So 90 to the power of 4th and pi over 8 minus 8 over 9 pi, then plus pi 90 squared over 2, then 120 minus 4 times 90 over 3 pi over square. Alright, so let's see what we got. Alright, so after putting in the calculator, this is what I got. So it's 92.3, or you might get 92.2, not big deal. And this have a unit of millimeter to the power of 4th. Okay, so that's going to be our semicircle. And remember, our original thought process is using this rectangle one minus this semicircle one. Well, let's look back. This rectangle one is super easy. We found out the first step in one equation. For the semicircle, it's kind of tedious. We have to use parallel axis theorem twice. We find the centroid moment of inertia first. So let's go ahead and put all those together. Very last step. Our I is going to be equal to I this rectangle minus this I semicircle. Our rectangle value is 1.38, or that's going to be 13.8 times 10 to the power of 7, or will be 138 times 10 to the power of 6, right? So it's 138 times 10 to the power of 6 minus 92.3 times 10 to the power of 6. And when we calculate them together, we'll get 45, about 45.9, because here it's 138.2, right? It's 138.2. So that's going to give us 45.9 times 10 to the power of 6 millimeter to the power of 4. All right, so that's for this problem, and hopefully that gives us a direction. When we have some common shape, we can just combine them together, subtract or add together. And however, do be mindful, the axis have to be the same axis, especially for this semicircle. In order to do that, we need a 2 parallel axis theorem to get it. All right, I'll see you next time. Have fun learning. Bye-bye.